Okay, welcome back. Now I'm going to do a problem with, I'm calling radiation of two spheres. I'm going to have two spheres. One is a gray color sphere like this, and one is a black color. Right now I'm warming up the black sphere. So let's measure the diameter of the sphere. So you can see here, I am warming up water, I'm boiling it, and then I have the sphere sitting on it. So let's measure the diameter of this sphere. Then I have a device here that measures the temperature, okay? It's called infrared thermometer. And the way that it measures temperature is that you point at it, it's a laser pointer, and you point at anything and it measures the radiation coming from that object, the infrared radiation, and based on that you can know the initial temperature of the metal. So right now if I point, at the metal, you see the red spot? So the laser helps you to see what object you're pointing at, and right now I'm pointing at the sphere, and it's showing me 59. It kind of is jumpy a bit, so if I go closer to it here, right now it's showing that the sphere is 95, 96 Celsius. So if I kind of point at different points along the sphere, the top of the sphere is a little bit cooler. The sides of the sphere, 96, 97. Let's see if we can kind of rotate the sphere. Okay. And now the top is going to be 94, 95. Okay, so let's assume the average temperature of the sphere is about 95. Okay. So then I can take this sphere out, start my stopwatch, and then I can ask, how long will it take that sphere to reach 50 Celsius or some other temperature, whatever temperature we want to choose. So right now it's starting about a 95 Celsius. So I'm going to take this sphere out, okay, start my stopwatch. Okay, so now I'm going to put the other gray sphere on there. I'm going to measure the diameter of the gray sphere also. And so let me get the gray one warmed up. The initial temperature of the black was around 95 Celsius. I've already measured their masses, and their masses were, the black one was heavier, and it makes sense because it's also a bit bigger, right? They're the same material, they're made of lead, so we can now use the specific heat of lead. A specific heat of lead. The question is, due to the radiation of heat that's going to be coming out of this bowl, how long will it take it to cool down to, let's say, 50 Celsius? And then we'll test our calculation. So power radiated is going to be sigma A E T to the fourth minus T of the surrounding to the fourth, right? Surrounding to the fourth. That's equal to minus the mass of the lead ball, minus mass of the ball, times the specific heat of the ball, times dt over dt, right? So then the sigma is going to be a certain constant, 5.6696 times 10 to the minus 8. The surface area of a sphere is going to be 4 pi r squared, 4 pi times the radius. So the black ball is going to be, the radius is going to be 3.7 centimeters, right? So 0.037 squared. The emissivity of a black color is 1, right? And then we have here all of this stuff, t to the fourth minus t surrounding to the fourth, is going to go down there. The dt is going to come up here. So dt is here, minus the mass of the ball, 1.58 kilogram. The specific heat of the ball is going to be 128 joules per kilogram Celsius. And the kilogram and kilogram cancel, right? And then we're going to do dt over t to the fourth minus the surrounding temperature is going to be, kind of use this infrared to also give us the surrounding temperature is about 26 Celsius, right? Just kind of touch something that's at room temperature. So it's about 26 Celsius, so that's going to be 299.15 Kelvin. 299.15 to the power of 4, okay? So then I'm going to be integrating this the initial temperature of the bowl, which was 95 Celsius. So if I add 273 to the final temperature, I'm asking how long will it take to reach 50 Celsius, right? So I put here 50, so 273 plus 50, 323.15, okay? Then I do this integral, multiply by this, and then divide by all these numbers, right? So let's see, my stopwatch so far is showing My stopwatch so far is showing 7 minutes. Let's see what the temperature of the metal ball is. I'm gonna lift this up and then point it at the ball. You can kind of see her still 85 Celsius, 86 Celsius. You see? So it's gone down 10 Celsius in 8 minutes. Okay, now I'm pointing it at the gray ball. Its initial temperature. Okay, it's about 94, 95. So its average temperature is about the same. Okay? Now, I'm gonna start the other ball going at the 10-minute mark. I'm gonna remove it because this one has already been cooling 10 minutes. It's now 9 minutes and 30 seconds. So at the 10-minute mark of the black ball cooling, I'm gonna take the gray ball out and put it on the table, and let's see how long it takes the gray ball to cool. Its initial temperature is also 95. So it's about 10 minutes now almost. Okay, now let's go over here. Besides the size of the gray ball being a bit different and its mass, the primary other difference is its emissivity. When you look up the emissivity of gray color, it comes out to be 0.87. So it doesn't emit as much and it doesn't absorb as much as black. So its emissivity is 0.87. So we're going to use that for the gray ball. So then what changes for the calculations? So you still have this thing, right? Then you have 4 pi. The radius is going to be bigger. So 7, that's going to be what? 0.03. And then over here it's going to be 385 squared. Okay? So since the diameter is bigger, it's going to tend to reduce the time because this number goes down to the denominator. If a ball is bigger, it tends to radiate more. It will tend to reduce the time that it's going to take to cool, right? So how about this? Here the mass is more, so that's going to tend to increase the time. So the mass is 1.7 kilogram. Okay? The initial temperature is about the same. The final temperature is the same. T to the 4th minus 299. The room temperature is the same. So all of this stuff doesn't change. It stays the same. However, because the emissivity is different, it doesn't radiate as much heat as this would predict. This is if the emissivity was 1, right? So now I have to put here the emissivity of gray, 0.87. So what is that going to tend to do? The 0.87 goes down here. It tends to increase the time that it takes to radiate away its heat, right? So black ball would radiate away its heat more, but the gray will radiate less, so it should take longer. So let's see what the calculations come out. 6 minutes. So it's about 4 minutes longer, right? That it should go down to 50. And now I am at the 26-minute 45 seconds, so I'm reaching 27 minutes, and our predicted time was 27.6 minutes, so it's almost 27 now. Let's point it at the ball. It is showing 47 and a half Celsius, 47 and a half different points. So that means we are in the vicinity of our answer, right? Right now it's 47, 47.9, 48, depends on where I point. So I'm almost in the vicinity of the 50 degrees Celsius. So the time that it took, 27.22 minutes. So that one is actually pretty good, pretty reliable answer. Okay, now I am approaching the 41-minute mark. And that means the gray ball has been cooling for about 31 minutes. So the time for the gray ball prediction was 31 minutes. It was 4 minutes longer than that. So right now it's 40 minutes, 53 seconds. So it's approaching 41 minutes. So let's look at the temperature of the gray ball right here. 51.1, 50 point, depending on where you point to, it varies a bit. So 51.1, 51.9, let's see if the other side, 50.7, right? 51.4. So we were hovering around that 50-degree mark. So considering all other things, the sources of error and the fact that we don't know the exact temperature, it worked out really, really well. The prediction that it would cool in 31 minutes is roughly around right. The other one, the black ball, cooled down quicker, and the prediction that it would cool in 27 minutes also worked out really well. So now you can see how to do these calculations and how to include the emissivity of the color of the ball or the other material, and how to do all the integration and the prediction of the time that it takes to cool, okay? So this is a pretty good video, pretty good demonstrations, and it teaches you a lot. Thank you very much.